All right. Good evening, everyone. Uh, I think we have the Amod event here. I hope most students will join soon. But anyway, we will start now. Uh, so this week we are going to talk about interpolation methodologies. What are the different ways of interpolating? And I think it is not the interpolation did not end here. It is going to continue for the next week also. So this week we saw mostly Newton's forward difference and backward difference, some basics before we enter into Newton's forward difference and backward difference formula. And also we talked about error functions, like how to find out what is the error from an approximating function. What is exactly the error from an approximating function? What is the error that you expect when you interpolate? So these are the things that we saw. Maybe we will quickly go through the lecture what we did. So I will just I will just give you a broader picture. So interpolation is nothing but uh, it's based on this Weierstrass theorem, and if your function is continuous in a closed interval, then it can be approximated as a polynomial, and for any positive number within that, you can find the value of that, and uh, or such that positive number epsilon, however small, can be represented like this, and xi's are so these xi points, which you are going to use it to construct a polynomial, is are called tabulated points, nodal points, or data points. Uh, Basically, you can call it however you want. So the first thing we saw is linear interpolation, quadratic interpolation, and then there are like two different methods of interpolation. Broadly, you can classify as one is either if it is equally spaced, whether the x's or xi's are equally spaced, or it can also be unequally spaced. So equally spaced methods are Newton's method and Gauss' method, and unequally spaced will be taught in the next week, which is Lagrange method and also Newton's divided difference method. So these are the broad classification of interpolation. And then we saw this finite difference operators, how you can express them. So if it is a forward operator, then the next function values minus the previous function value is your uh, current. The next function value minus the current function value is your current forward difference value. Okay. Similarly, the backward is from the previous value, and then central is in between. So from h by 2 to minus h by 2, and similarly averages, you know how to average. And finally shift operator, this is an important operator because it just shifts from one function value to the next, and you can express all the above uh, you know all these four operators with just shift operator, and we expressed it like this. And then there is also called differential operator, which we didn't start get into detail now. In future weeks you will find this. Okay. um, and then we try to use the shift operator, how this shift operator can behave. We saw all these, and then we also try to express one operator in terms of other. If it is delta, which is forward difference, then you can express in terms of shift operator as e minus 1, or if you want to express in terms of backward difference operator, you can express it like this. In terms of central difference, in terms of ht, you can express it like this. So there are various ways you can express each and every operator, so that table is provided here. And then we saw like a theorem where nth difference of f of x equal to x power n is simply n factorial times h power n, where h is the spacing between the x values. Okay. um, so this we saw. And then the forward difference, how it works, and also the backward difference. Here it is placed in between, but for convenience we just place it on the same line. So we'll see that while solving the problem. Similarly, backward difference, how to do it, and also central difference. So basically forward difference usually comes in the first part. Whenever you want to find a value, interpolate between the first few initial values, first few initial xi's, then you would use forward difference. If it is a backward difference, then if you are in the last few values, then you use backward difference. I mean, this is the best way you can use backward difference, which will give you accurate results. And similarly, central difference, if it is somewhere in the middle, you are trying to interpolate. And then we saw for Newton's forward difference formula, and we saw an exhaustive material on this, how to derive and how the error is calculated and all these things. I'm not getting into details. I'm just providing you an important uh, you know equation or formula that you may need to remember while solving problems. Okay. um, this is how you express Newton's forward difference formula, where it is expressed as y naught p delta here is a forward difference operator, delta y naught plus like a Taylor series expansion. Similarly, the p here is x minus x naught. X is the value that we are interpolating for. Okay, so you will be given a set of x values, and you will be asked to find for one x value, which will be somewhere between these set of values. So where you need to do interpolation. Okay. um, so this is so that x is this, and h is this is a equally spaced. So as I said, Newton's forward difference and backward difference is for equally spaced xi's or equally spaced data points. So in this case, the h does not vary for each and every data point, so that's why we take it like this. And similarly for backward difference, you will have p plus 1 by 2 factorial, p plus 1, and things like that. In forward difference you have p minus 1, in backward difference you have plus. Okay, that's the difference. And similarly here xn is the last data point in the table. Okay, and then errors, errors for this approximation can be either expressed as two things. One is uh, the polynomial. So for a given function, we don't know what is the function is. It has been tabulated and given it to you. So there is a polynomial that we fit for. So that is p of x. Okay, but this function is not exactly the polynomial. So the difference between y of x and p of x is your error. Okay, so that error you're trying to express in terms of two quantities. One is w and one is the other function here. The reason to divide these two is the w will be associated to only the polynomial. So for example, w will be associated only to the values in your data points. So for example, x minus x naught, x minus x1. So basically what it tries to do is, whenever your x, the interpolating value that you're trying to find the function for, if you evaluate that uh, so let's say that x is equal to x naught, then the polynomial will give you the right answer, right? Then you do not have error, your error is 0. So in order to take that into account, you have this w of x. So this function, what it makes is, it makes your error to be 0 in those nodal points. So that is why this function is expressed as x minus x naught to how much k is the number of data points that has been given for which you fit the polynomial. So in that way, this w of x will make this error to be 0 in those data points. However, this will not be 0 in the other places. For example, the places where you are interpolating, it will not be 0, and that function is expressed as f k plus 1 zeta and k plus 1 factorial. So this is just to give an idea of what this error is and how you can express that. Okay, so if you are more interested, please feel free to check out the lectures. Okay, and the other thing that we saw is, till now we were talking about interpolation, but there is also something called extrapolation. You call this extrapolation. I mean, basically there is not much of a difference. When you are trying to find a value for a data point or for any point for any x, but it is outside the given table. Okay, if it is outside the given table, if it is uh, comes after the last xi, in this case let's say xk, if it comes after that, then it becomes an extrapolation, or it comes before x naught, then it becomes an extrapolation. So these are the two places where you use extrapolation. So you can do extrapolation with the same set of formulas, with the same Newton's forward difference or backward difference. There's no problem. But only thing is you need to use xp as x. Okay, you just express it as a functional form in terms of x, and then p as x minus x naught by h, and you get a polynomial. So you use the forward difference formula, get a polynomial, and then evaluate the x, uh, and then substitute the x, and then evaluate the f of x. So that will give you the extrapolated what do you call value. So that's where we will see one problem of extrapolation, just to give you an idea. And then we got into central difference, but I think only one lecture was there. So probably we will come back to central difference maybe next week. Okay, so I will skip this central difference for now. So for now, today we will deal with only forward difference and backward difference interpolation, and also about getting the polynomial. Okay, so before that, let me check if there are any questions. So Hasana is asking to upload last week notes. All the notes are already been uploaded. For example, maybe I will show it to you where you can access them. So you can go to my courses. You can go to the course. So if you go down here, you have a problem solving session. There is a recording, right? So you open this. You will have a click here option here, which will take it to the Google Sheet like this. So here you can find the presentation folder, the drive folder link. You can open this drive and then you can check there. I used to upload all the lectures, all the week, these presentations. There you can go and access them. Okay. All right. So mostly I will upload them as soon as I complete the lecture, maybe like 6:30 or 7 p.m. on the same day. Okay. All right. I hope there are no doubts. If there are any doubts, please stop me in between. Let me check my recordings. Okay. It's very good. So today what we are going to do is I have 4 problems, and these are simple problems. It's not it does not involve a lot of calculations, so that's why I increased the number of problems. I have 4 problems today, and they are going to deal with mostly forward difference, backward difference, one on extrapolation, and also one on constructing the polynomial. So to do extrapolation, you will construct a polynomial. So in that way, it helps you that way. And I hope that is sufficient enough for you to at least attend assignment 4, and also I hope it will be helpful for you if you get this hands-on training. All right. If there are any questions, you guys know what to do. I will go forward and solve the first problem. So the first problem is about to find a missing term in the following table. So you have been given x and y. So there are like 5 data points of x, and only 4 values for now. But you need to find out, or you need to find out this one, right? So they are asking you, if x is equal to 200, what is your y value? So that you need to find this missing term. Okay. But you have been given 4 data points. How do we proceed this problem? If you have any ideas, please let me know. So what the question says is, we have 4 known points. Okay, so that we know. We need to find what is y at x is equal to 200. This is what we have been asked for, right? So since we know 4 points, what we can do, we can use a polynomial to fit these 4 points, and then try to get uh, uh, you know x, try to get value for x is equal to 200. Okay, that is one way. So what we can do, so since we know 4 points, if we know 4 points, what is the degree of polynomial we can fit? So if you have n points, you can fit only n minus 1 degree of polynomial. So if you have 4 points, you can fit third degree polynomial. Okay, and if you can fit third degree polynomial, what we know about third degree polynomial is it's fourth order, or fourth what do you call, fourth order difference. Fourth order difference is 0, which means basically I'm telling del power 4 y is equal to 0. Okay, so if you keep doing the difference for a third degree polynomial, the fourth order difference is 0. So if that is the case, we can express this as del power 4 y naught is equal to 0. Okay, and we can write del power 4. So del is delta operator is actually e minus 1, right? E is a shift operator, so if I can replace it like that, this will be e minus 1 4 y naught is equal to 0. Okay, so I'm trying to express all these data points in a polynomial form. So for that, I'm going to use this functionality of difference, fourth order difference is becoming 0. So that will give you a polynomial, and that will be helpful for you to find x is equal to y at x is equal to 200. So how do we express this e minus 1 power 4? We can use binomial theorem to express this. What is binomial theorem? So if you have e minus 1 power 4, then you can write it as summation k is equal to 0 to 4 factorial divided by k factorial into n minus 4 factorial into e power n minus, or in this case it's 4 minus k times 1 power k. Okay, so you do this summation. So this is okay, maybe I will write it in general form so that you will understand. A plus b power n, you can write it as summation k is equal to 0 to n, yeah, 0 to n factorial divided by k factorial n minus k factorial a power n minus k b power k. So here I am just taking, so there should be minus 1. Here I am taking a to be e and b to be minus 1. So this will easily expand your polynomial e minus 1 power 4. Okay, this is a binomial theorem. I hope you guys already know. So if this is the case, then how do we express this? Then we can write, so let's say for k equal to 0, then it becomes 4 factorial divided by 0 factorial is actually 1, and then this should be not n minus 4, this should be 4 minus k. So then this will be 4 factorial e power 4 minus 0 minus 1 power 0 plus 4 factorial. Kadiravan, do you have any questions that you want to ask? Okay, maybe I'm muting. I'm going to mute you. If you have any questions, please let me know. You can unmute yourself. So I thought it might be by mistake. Okay, so now if you make k to be 1, it's going to be 1 factorial times 3 factorial e power 4 minus 1 minus 1 power 1 plus 4 factorial. But if you guys know what is e minus 1 power 4, if you know the formula, you can write it, but I'm just going through every step. So this is going to be 2 factorial e power 4 minus 2 minus 1 power 2 plus 4 into this is going to be 3 and 1 e power 4 minus 3 minus 1 power 3 plus 4 into 4 factorial 0 factorial e power 4 minus 4 and minus 1 power 4. So if we can write this as, so this you can cancel, this also you can remove. 1 for 0 factorial is just a 1. So if I write them out, it is going to be e power 4 minus 1 power 0 is 1 plus this is going to be 4e cube into minus 1, so I'm going to put minus 1 here, and then this is going to be plus going to be 3 times 4 divided by 2 e square minus 1 square is 1, and this is going to be 4e into minus 1, so I'm going to put minus plus 1. Okay, so this is, you can do this. So e minus 1 power 4, we can write it as e power 4 minus 4 e cube plus 6 e square minus 4 e plus 1. So what did we start with? We started with e minus 1 power 4, y naught is 0, right? So if I substitute it here, this is going to be e power 4 minus 4 e cube plus 6 e square minus 4 e plus 1 into y naught equal to 0. Okay, so we can write this as e power 4 y naught. And what is e power 4 y naught? So maybe if I want to write it, e power 4 y naught is e power 3 y1, which is equal to e square y2. So basically I'm going to shift from y naught to y1, y2, and this is a shift operator, right? And if this is the case, then it's going to be e y1 equal to, sorry, from y2 y3 and then y4. So e power 4 y naught is nothing but y4. So if I do this, so e power 4 y naught is y4, then similarly 4e3 is going to be y3, okay, plus 6 e square y naught is going to be y2 minus 4 y1 plus y naught equal to 0. So basically what I did is I had we had 4 data points. Now I expressed a polynomial with these values, so y naught, y1, y2 and y3, and we know this is going to be equal to 0. So in this we know 4 things, we can find the 5th one. So basically that's how I fitted the polynomial. Okay, so now yeah, we need to start somewhere, right? So what do we choose as y naught? So since we are here, we can choose this as y naught, this as y1, this is y2, y3, or maybe sorry, this is y0, y1, y2, y3, and y4. So we used all the data points in order to get the now we can express the other data points in terms of this. So should I write it again? Maybe. So I'm going to say this is y0, y1, y2, y3, and y4. Okay. So then we can write this as, we wanted to know y3, so let me rearrange this. So if we take y3 on the one side, this is going to be y4 plus 6y2 minus 4y1 plus y0 divided by 4. Okay, that's it. So now you just substitute these values, you will end up with the answer. So can someone substitute and let me know what the answer is? It's going to be 9.31 minus 4 times, did I do it right? Yeah, minus 4 times y1 is 6.78 plus 4.52 divided by, how much is the answer is going to be? So numerator is something like 49.8 I'm getting, divided by 4 is 12.45. Okay, I'm getting y3 to be is 12.45. So you can check whether this is right by just seeing how it varies. So you can say it is at 9.31 and reaches 16.54. So you expect it to, lie between 9 and 16.54, and that is what exactly we got, which is 12.45. Okay, is this clear how we did this problem? We use this forward difference operator technique to fit this third degree polynomial. So we call this curve fitting in, maybe in advanced subjects like finite element methods, FEA or CFD. We call this curve fitting. We not just fit, you know, uh, just randomly. We also sometimes take care of the directionality. So what are the values that we need to take in front? How many values we should take in the back? And based on that, we get different polynomials. And each polynomial will tend to behave differently while you integrate them within the framework. Okay. All right. It's pretty straightforward, I guess. I hope there's no questions till now. So if there are no questions, then we will go forward with the second problem. So in the second problem, it's same as first problem, and in addition to it, we found that it is 12.54 here. Okay. Now, what the question is asking is, find the interpolating polynomial using Newton backward difference. Now, you will use Newton's backward difference to find the interpolating polynomial, and we will find a value for x is equal to 300. Now, which means this is an extrapolation problem. We need to find what is your y value at x is equal to 300, which is outside the data point which has been given for us. So then this is called as an extrapolation problem. Okay. Now, to get the interpolating polynomial, we were asked to use Newton backward difference So if we go back to the backward difference formula, so we will be using this formula here. Okay. Should I copy, or I'll just write it once. So what the Newton's backward difference formula? Maybe NBDF. I don't know how to call it in short form. So this is going to be y of xp equal to y of n plus p nabla y of n plus p into backward is, I guess, p minus 1, no, p plus 1 by 2 factorial. Is it right? Yeah. P plus 1 del square y n plus p into p plus 1 into p plus 2 divided by 3 factorial del cube yn, plus similarly you can keep on doing this. Okay, this is your backward difference formula. Now we need to choose x naught. Okay, so here it is xn, so your xn is going to be your final value here 250. Okay, and in order to find the polynomial, we keep xp to be x, so that you will get a functional form. So you keep xp to be same as x, and h is, what is the difference between, let's say, xn minus xn minus 1. So that is the h, which is 50. Okay, 200, 250, 100, 150. So if this is the case, then p is going to be x minus xp divided by h, which is x minus x minus xn divided by h, which is x minus 250 divided by 50. This is your p. So now we already know p, we just need to substitute it here. Okay, but we don't know what are these values, delta, like nabla yn, nabla square yn, nabla cube yn, all these things we don't know, right? For that we will write the backward difference table, and from there we can find out that. So x and y, what is x and y? 50 to 250, 50, 100, 150, 200, 250, and y is 4.52, 6.78, 9.31, 12.45, which is what we found, and 16.54. So now we need to find nabla y. Okay, so here it's a backward difference. So for the first x and y, we do not have any preceding value, so this place will be empty, we don't know that. Now for the second one, the present value minus the preceding value is your nabla y. Okay, so if you do that, what happens? If you do that, it's going to be 6.78 minus 4.52, which will be 2.26. And similarly, 9.31 minus 6.78 is going to be 2.53, and 12.45 minus 9.31 is 3.14, and 16.54 minus 12.45 is 4.09. Okay, now del square y, or nabla square y. Now the same story. This one does not have a preceding value, so this place would be empty. You should start from this place. So then what happens? 2.53 minus 2.26, which comes out to be 0.27, and 3.14 minus 2.53 is 0.61, and this is 0.95. Okay, now you just have to repeat it until you exhaust the values. So del q y is going to be so again same, this will not have anything, So this is going to be 0.61 minus 0.27, which is going to be 0.34, and this is also going to be 0.34, and then you find del power 4y. So here this one again does not have it. So for the final one, you have 0.34 minus 0.34, which is 0. Now this is where you stop because you do not have any more data to continue this backward difference. Okay. Now what we chose is we chose xn to be 250. So which means you are going to choose this value. If you're choosing this x, then you have to use corresponding delta y's and del square y's, del power 3y, or del means in this case nabla. Okay, so let's because if this is xn, this is going to be your yn, and this is going to be your nabla yn. This is going to be your nabla square yn. This is going to be your nabla cube yn. This is going to be your nabla 4 yn. Okay, since we already know that this is I mean, we fitted polynomial for the third degree polynomial, and we took del power 4 yn to be 0. Here it automatically gives you that since we were able to fit those data points, your del power 4 yn at the last point is coming out to be 0. Okay, some interesting fact for you guys to think about. Now let's substitute it. I think we have everything. We do not need to do this del power 4 because the del power 4 is 0, so we don't need this. So we need only these 4 terms. Let's use this. Let's do this. So it's going to be y of x. It's going to be yn. What is yn? 16.54 plus p. What is p? X minus 250 by 250. Sorry, x minus 250 by 50. P into delta y1, which is 4.09. Correct? And then p plus 1 by 2 factorial, which is 1 by 2. P is x minus 250 by 50, and x minus 250 by 50 plus 1. This is p into p plus 1 divided by 2 factorial into 0.95. Okay, and then you have 1 by 6 p plus 1 or minus 1? Yeah, plus 1. Okay, and x minus 250 by 50 plus 1. I do not have space here. I will write it in the next. Where should I write it? Plus 1 by 6 x minus 250 by 50 x minus 250 by 50 plus 1 x minus 250 by 50 plus 2 into 0.34. Okay, this is 3 factorial. 3 factorial is 6. All right. So now you can simplify this, express it in terms of x power, x cube, x square, and things like that. And you can perform this thing. You can also do one more thing. Okay, so let me show you that. So in order to simplify this whole expression, you can maybe write a transformed variable x per x dash. X dash is nothing but x minus 250 by 50. Okay, if you write it like this, what happens? Your table becomes simple. I mean, it's just setup. It's just for convenience. I doing this. So if you write it like this, then x dash becomes this becomes 0 because 250 minus 250 is 0. This becomes minus 50, so this becomes minus 1. Similarly, This becomes minus 2, this will become minus 3, this will become minus 4. Okay. Now your polynomial will look a little bit simpler in terms of x bar. So then now you take, so instead of xn, it will be x bar n. So in this case, p is going to be x bar minus xn bar divided by h. Here h is nothing but 1 and x bar n is 0. So your p will simply become x bar. Okay. So now you can express the equation y in terms of x bar is going to be y naught, which is 16.54, plus p, which is simply x bar times 4.09, plus how do you write this one? X bar into x bar plus 1 into 0.95 plus x bar into x bar plus 1, okay, divided by 2, x bar plus 2 divided by 6 into 0.34. So now this becomes much simpler, right? That's why we can write it like this. Now what I've been asked is we want to find what is the value for x is equal to 300, right? For x is equal to 300 was y. So first you can find x bar. X bar is x minus 250 by 50, which is 1. And so y is going to be y of 300 is going to be, or in this case, y at x is equal to 300 and x bar is equal to 1. Both are same, one and the same. Okay, which is going to be 16.54 plus 4.09 plus 1 into 2 by 2. So it's going to be 2 by 2.95 plus this is going to be 1 into 2 into 3 by 6. So it's going to be 6 by 6 into 0.34. So you can simplify this. This will come out to be 16.54 plus 4.09 plus 0.95 plus 0.34. Okay. How much does this come out to be? So something like 21.92 is what I'm getting. Okay. So here, if you look at it, if you go back to this problem, you have, you see it is increasing from 16.54. So till now it has been increasing. So at 300 we expect it to be more than 16.54, and that's what you see here. It's going to around 21.92. Okay. So basically we have like third degree polynomial which can interpolate between these values also, which is, so the third degree polynomial is this one. Okay, or this one, both are same. You can simplify them, it becomes third degree. So you can see that you have x multiplied 3 times, so it's going to be, this is your highest degree you're going to get in this equation. So it's going to be x cubed. So this third degree polynomial you are able to get from the Newton's backward difference formula, and you are able to extrapolate from the polynomial to this value 21.9 for 300. Okay, any questions? I guess interpolation is not new to for any uh, let's say BTech student or so, because they might have done it even in the high school days, right? But here it is more in general, like you might have fitted like a linear line between 2 points, and you would have found what is the value in between. Okay, But here we are trying to make it more and more appropriate, more and more accurate, based on the available data that we have. Okay, so that's why we have multiple values here. All right. There are no questions, I guess. Still, um, maybe I will solve the third one. So the third one is a typical interpolation problem, where you have, a following table is given, where y represents the distance in nautical miles of the visible horizon for any given height. So at 100 feet, this is your distance of visible horizon, and as you increase the heights to 300 feet, your visible horizon distance has also increased uh, to 18.42 nautical miles. Okay, so now this height is measured in Earth's surface, but these are all not relevant to us. Only thing is we need to use forward difference interpolation formula and to find out what is the distance at 160 feet. So let's say, where is this 160 feet? Between 150 and 200. At 160 feet, what will be your height? What will be your distance of visible horizon is what you need to know. Okay, and for that we are going to do uh, apply forward difference interpolation formula to get that. Okay, all right. Newton's forward difference formula. Okay, so maybe we will first draw the table, or make the table. So first is you have x and y. You have 100, 150, 200, 250, and 300. Then your y is 10.63, 13.03, 15.04, 16.81, and 18.42. Now, since it's in forward difference, you have delta y. Okay, and delta y. Uh, so for forward difference, you are going to use the next upcoming value, function value, to find the difference at the present, uh, you know, present data point. So that is why it's called forward. You look for the next value. So in this case, what you have 13.03 minus 10.63 is what you have to put it here. So let me quickly write that down. So 13.03 minus 10.63. You can parallelly do it yourself and let me know if I'm doing it right. So this is going to be 2.01. This is going to be 1.77, and this is going to be 1.61. And then similarly you can do del square y. Here it is going to be 2.01 minus 2.4. So you need to mind the sign here, which is going to be minus 0.39. So this is lower than this, so it has to be minus. Similarly here again it is lower, so it's going to be minus 0.24. This is minus 0.16. Okay, similarly we can do delta q y. Here the upcoming one is lesser, so it's we expect it to be positive, so it's going to be 0.39 minus 24 is 15. So, and then this is 8, 0.08. Okay, now the final one, del power 4y, is going to be 7, 0.07, but with a negative, minus 0.07. Okay, this is your forward difference table, and we were asked to find what is the y value at x is equal to 160. So 160 is somewhere between this and this. So 160 is over here. So 160 is somewhere here. 160 feet. So your XP is going to be 160. Now, which value to choose? Should we choose this 200 or should we choose 150? Right, that's the question. Since this is a forward difference formula, you should choose, you're trying to predict the upcoming value with the present value. So which means you should choose 150 and predict the 160 feet. So in that case, your x naught is going to be 150. Your x naught is not the initial value in your table, but the value in between what you look for. So this is going to be uh, this is going to be your xp, and this is going to be your yp, and similarly nabla of yp, nabla square of yp, nabla cube of yp, and etc. But however, nabla power 4 of yp is not present, so this is not here. Okay, which means you should not use it. You cannot use something like this here. Okay, you should just use it. So you should use only these values along the table. All right. So now it's time to write down the power difference formula, which is y of xp is equal to y naught plus, what is the formula? P delta y naught, P delta y naught plus p into p minus 1 by 2 factorial delta square y naught plus p into p minus 1 into p minus 2 by 3 factorial delta cube y naught plus, we do not have delta 4, so we no need to write that. Okay, but it's a good idea to write one more extra term, but anyway it's going to be of no use because you will multiply it with 0, or it is not present, so you have to cut that off. All right, now we need to find what is p. First we understood what is x naught. X naught is 150, and the corresponding y naught we can get it from the table. Y naught, delta square y naught, everything we can get it from the table. And our xp is 160 feet, which is what for which y value we seek for. And h, what is h? H is, you can see it is going for every 50 feet in height. Okay, so h is going to be 50. So if that is the case, p is going to be x naught minus xp divided by h. Correct? Sorry, x minus x. Sorry, the other way. xp minus x naught divided by h. xp is 160 minus 150 divided by 50, which is going to be 10 by 50, which is 1 by 5, which is 0.2. Okay, so your p is 0.2. Now you have everything in this formula. You can just substitute p delta y naught, delta square y naught, delta cube y naught, everything you can substitute it to get y at. So you should note that it is at 160 feet. So let me write that down. So y at xp, which is 150 feet, is equal to y naught, which is 13.03, plus p is 0.2 times 2.01 plus 0.2 into 0.2 minus 1 divided by 2 into minus 0.24 plus 0.2 into 0.2 minus 1 into 0.2 minus 2 divided by 6 into 0.08. Okay, let's substitute this. So what happens here? This is 13.03. So 0.2 times 2.01, which is 0.402 plus 0.2 into minus 0.8 by 2 into 0.24 into minus 1 This is 0.0192 plus, what is the final value you guys are getting? Just taking some time. Minus 0.8 into minus 1.8 divided by 6 into 0.08. This is 3.84 to 10 power minus 3. If you just add them up, 13.03 plus 0.402 plus 0.0192 plus 0.0038. This comes out to be something like 13.45. Okay. So which is 13.45 nautical miles is what you see at 160 feet. So from 13 it is goes to 13.45 at 160 feet, and it goes to 15 at 200 feet. So that's it, simple. You just need to construct the table, this table. You should know what you're using, forward difference or backward difference. If it is backward difference, it's going to align in the descending order, right? So we saw that in the previous problem, it is going to align something like this. So if it is a forward difference, it's going to be something like this. So once you construct this forward difference table, you just have to use the forward difference formula. You find out appropriate x naught and xp. So the important point is this p you have here, p should lie between 0 and 1. Okay, uh, it cannot be more than 1. That is the important pointer. That's why we chose x naught to be 150. If you would have chosen x naught to be 100, it will become 100 minus 160 by 50. Then it will be 1.2. So that is not appropriate. Okay, so you have to choose the x naught in such a way that it comes between 0 and 1. You cannot choose 200 also. If you chose 200, it's going to be minus 0.8. Okay, it is outside 0. So for forward difference, this p should be 0 less than 0 less than p less than 1. That is the condition you should have satisfied. For backward difference, it's the reverse. It's going to be minus 1 less than p less than 0. Okay, this is the for backward difference. This is how you should. So for this case, let's say, so this case is not required. Maybe the next problem is our backward difference. You will know here for sure. Okay. So there are no problems till now. Are there any doubts? All right. I hope these are straightforward for you. Now the fourth question is about the same thing we did for forward difference. Now we are going to do it for a different set of numbers but using backward difference. Okay, so the tabular values are like varying from 1 to 2.5, and the corresponding f of x is given, and we were asked to find what is f at 2.25. 2.25 is somewhere lying at the end of the table, and hence it is better if you use a backward difference because you can cover a lot of value. So if you use, so let's say if you use forward difference for this case, what you will be left with is, so here you have 4 values, right? So you will have only 4, and you will have this as your table, and the fourth value, this value will have only these 3 y, delta y and delta square y. So you have only 3 variables to deal with. But however, if you have a backward difference, you will have similar to, like, you will have 4 values so that you can get a more accurate uh, you know interpolation value for somewhere at the end of the table. Okay, that's why we use backward difference in this case. It's not like this is right, that is it is right or wrong. So you can actually do forward difference for this case also, and you will be able to get an interpolation value, but that interpolation value may not be as accurate as whatever backward difference gives. So that's why you should choose which method to use at appropriate places. Okay. All right. So um, so for this table, we do the usual steps. We first construct the table. Let's write that down. X and F, which is 1, 1.5, 2, 2.5. Okay. And F is going to be 2.7183, 4.4817, 7.3891, 12.1825. Okay. Now, since it's a backward, I'm going to use nabla F, and as I said, for this it does not have a preceding value, so this will be empty. So from here you will start. So 4.4817 minus 2.7183. How much is this? 1.7634. 7.3891 minus 4.4817. This is 2.9074. This is 12.1825 minus 7.3891. This is 4.7934. Now you can also find del square f. That is going to be 2.9074 minus 1.7634. So here you do not have, here you do not have. So it will be 1.144, and 4.7934 minus 2.9074 is 1.886. All right, we can also do nabla cube f. So these things will not be there. 1.886 minus 1.144, 0.74. So this is where it stops. We cannot do it anymore. We cannot do del power 4f. Okay. All right. So once you find this table, what we are asked to find, f of 2.25. So you can take xp to be 2.25, and xn. So this is a backward difference. So you have xn. Xn you can take it to be 2.5. Okay. So there is no other option. You have to take 2.5. You cannot take 2 in this case. So let me show you why is that the case. So xn, if you take 2.5, what happens? Your h we know it is 0.5. H is 0.5. Now p is going to be xp minus xn divided by h, which is 2.25 minus 2.5 divided by 0.5. This will be 0.25 by 0.5. Should be 0.5. Sorry, minus 0.5. Now this is the p which lies between -1 less than 0. This condition is satisfied. So you should select only this 2.5. If you would have chosen 2, what would happen? This becomes 2. If you make this 2, then this becomes plus 0.25. This becomes plus 0.5. That does not lie in between these values. So you have to take xn to be 2.5. So when you take xn to be 2.5, you have 4 values here to predict a more accurate value for 2.25. So that is where the advantage of backward difference comes. If you would have used forward difference, you had only 2 values to do that. Okay. So why do you can also give it a try. If you do forward difference, what will happen? You can check. Okay. So now, yeah, let's write down the Newton backward difference formula, which is y of xp equal to yn plus p nabla yn plus p into p minus 1 by 2 factorial. I think p plus 1 by 2 factorial nabla square yn plus p into p plus 1 into p plus 2 divided by 3 factorial nabla cube yn plus we have till nabla cube. Okay, so since this is written in terms of f, let me just be consistent. So f of xn, you can also call it y. There's not much of a difference. Okay, let's substitute everything. F of xn is 12.1825, 12.1825 plus p is minus 0.5, minus 0.5 into lambda of fxn is 4.7934, 4.7934 plus this is 0.5, and zero point 0.5 plus 1 is 0.5, plus 0.5 divided by 2 into what is this, 1886 plus 0.5 plus 0.5 and minus 0.5 plus 2 is 1.5 divided by 6 into 0.74. 0.74. Now what will happen f of xp? Can you guys find this out? 12.1825 plus 4.7934 into 0.5 minus 2.3967 plus this is also minus 0.5 into 0.5 into 0.5 divided by 2 into 1.886. So this is a minus 0.2358 plus 0.5 into 0.5 into 1.5 into 0.742 divided by 6. This is also minus 0.0464. Okay, 12.185 minus 2.3967 minus 0.2358, 4.0464. This is 9.5036. Okay, this is your for what? 2.25. So this is what you get from backward difference formula. Let's say if you do forward difference, what will happen? Let me copy this. So now this delta f is going to be the same thing, but a little bit above. This is going to be here, and then del square f is going to be 1.144, 1.886, and del cube f is going to be 0.742, right? 742. Okay, this is how your forward difference will be there, and for this you will have to choose 2, and if you choose 2 you have only left with these 2. Okay, so why we chose 2? For example, let's say you take your x naught, to be 2, and h is again 0.5, and xp is 2.25, which is what we want. So your p becomes x p minus x naught divided by h, which is 0.25 by zero point 0.5, which becomes simply 0.5. So this p is satisfied. So it is 0 less than p less than 1. So this is satisfied. Okay, this is satisfied. So which means you have to choose x naught to be 2. And when you do that, let's say you write your y of 2.25, sorry, f of 2.25 is equal to f of x naught plus p uh, f of x naught plus p into p minus 1 divided by 2 factorial del square f of x naught. Now what happens? Uh, you do not even have this one. You don't even have this. So this part is also 0. So let's say if I write that down, this becomes 7.3891 into zero point 0.5 times 4.7934. So which basically becomes between 2 and 2.5, you are just doing a linear interpolation. That's what you're doing. From 2 to 2.5, you're doing a linear interpolation. That's why it has reduced down to just these two values. I can even rewrite it in terms of linear interpolation. Uh, you know, in terms of this linear interpolation, your p is nothing but this part, your p, and then this is nothing here, this forward difference. Okay, this is a simple linear interpolation. Okay, so let's say if I do this 3891 should be plus 8. 0.5 into 4.7934 plus 7.3891. So this is 9.7858. Okay, now check these two values. So you can see from Newton backward difference, you have f of 2.25 to be 9.5036, and from Newton forward difference, you have f to be 2.25 with 9.7858. Okay, so in both the cases, it's not like you know this value is wrong. This is not like this is wrong. Okay, but it is erroneous. Okay, in numerical methods, there is no such thing called right or wrong. It can be more erroneous. For example, for this Newton forward difference is more erroneous because you just used linear interpolation. Basically, this is linear interpolation. So your forward difference formula is boiled down to simply linear interpolation. So when you have lower order interpolation, then it is more erroneous. This is an higher order interpolation. In this case, you have used. So if you check these values are coming from 2. If you check this value is coming from this value, and this value is dependent on this value. Okay, so in this way, and this one is felt from entire table. So this entire table, entire f value is been used to find out the value at 2.25. Okay, so all the variables are used to find out the value at 2.25. So in this case, this is expected to be more accurate. So 9.5036 is more accurate than 9.7858. Although both of these values lies between 7 and 12. Okay, although both of them lies between 7 and 12, and the mean of this 7 and 12 is 9, right? 7, 12, 19, 9.5. So mean is around 9.5. So we expect to be around 9.78 or 9.5, around that. Okay, and that is what we get. but the forward difference is a little bit erroneous. So it could be this is more erroneous. More erroneous than Newton backward difference. Now, this is not the same in the previous problem. In the previous problem we chose this value. Maybe in this case, maybe what you guys do is you try to do for backward difference interpolation for the same problem, and then evaluate at 160 feet what is your answer. Okay. In this case, uh, both forward difference and backward difference might work, and it 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 may give you same results. Okay, so it may give you same results, but you give it a try. But let's say you have to find out what is at 130 feet. For 130 feet, you will use these values. When you use these values, it will be more accurate. But if you do backward difference, you will be left with only two values to use, and in that case, your result is going to be erroneous. So it's not like forward difference is erroneous or backward difference is erroneous. It's about where you apply it. Okay, if you apply it at the initial stages, forward difference is better. If you apply it at the later stage of the table, backward difference is better. Okay. All right. Any questions? I guess there are no questions. I had 4 problems and I solved all those 4. And yeah, I think we are very quick today. So if you have any questions, you can ask me. For the next class, we will be doing uh, central difference, I think, and also Lagrange interpolation, and also Newton's divided difference formula. So we will work out problems on those three, those 3 methods. We will work out those problems. And for this class, yeah, these are the problems I have. So how many students do we have today? Yeah, it is understood. Thank you, sir. Okay, thank you, Pradeep. I think we have like four students. Yeah. All right. So I will stay in this meeting for another 40 minutes or so. And if you have any questions, you feel free to ask. I will upload these lecture notes in the Drive folder and also these recordings in the YouTube. Uh, you can look at it. And yeah, if there are no questions, then uh, yeah, then we can meet next week. Thank you very much for joining.